So this one's going to look a little different, guys, because we're going to jump on Desmos here in a minute and look at some graphs. But what I have here on this page is just sort of a review of some of the notes I've done with you in the past. So if you want to read through this in your own time, you can. It's basically reviewing how do we know two things are inverse via graphs, tables, or equations, the definition on how to check, and then if you want to use a test point to kind of do a quick check versus plugging in x and then using composition of function. So that's just a little bit of review for you guys if you'd like to look over it. Okay, so we have D, which is about one-to-oneness, and how do we use that to help us talk about domain and range of inverse functions. That was part A. So we had the vertical line test. It tells us if something we graphed, some relation, is actually a function. And then we think back and we also had the horizontal line test. Whoa, blaster in the past. Which determines if a function's inverse is also a function. So here's an example of a couple. This one right here, it would pass the vertical line test, and then it would also pass the horizontal line test, which means that this cubic function here is not only a function, but its inverse would also be a function, so it has an inverse function. Here we have a quadratic, which we know passes the vertical line test, but it doesn't pass the horizontal line test. We have two x's for one y, which means that even though a function, this happens to be a function, its inverse would not be a function unless we restricted the domain. And the way we always restrict a domain is to only look at a portion in which it's always decreasing, or, so we could restrict it from there to there, or always increasing. So either of those restrictions would work to talk about how to make this inverse of a function into an inverse function. Together, the horizontal line test and the vertical line test verify that a function is 1, 2, 1. Okay, which means that for each x and each y, there is only one corresponding y/x, and then these two go together and these two go together. Right, so for each x there's only one y, and for each y there's only one x, 1 to 1. So here's that same quadratic we were looking at. Here's if it's restricted where x is greater than 0, and here is it restricted for x less than 0. Okay, we're going to look at the big one, the one that always tends to throw you guys off, which are the trig functions. Okay, when we remember what cosine looks like, so remember we're going to be looking at cosine and cosine inverse, so I'm going to jump to my Chrome so that you can look at this graph. So hide that. So when we look at cosine, we can really clearly see that cosine is definitely a function. There's a vertical line here, a vertical line here. Nowhere that I draw a vertical line am I going to hit more than one point. So for every x, there is only one y. But if I were to take this guy and reflect it over the line, y equals x, you can see that each point, when reflected, is going to create kind of a wave that goes like this. Woo, there's our wave, right? But we can't do that, because if we do that, then we're not talking about an inverse function. So we can restrict it to some portion of the graph where it's always decreasing or always increasing. So we're going to do, I think that the computer does it from here to here. So from peak to minimum, maximum to minimum. So let's look and see. Yep, that's exactly what they do. No, it's not. Yes, it is. So here they have the 0, 1 that corresponds to this 0, 1. And then down here they have, this must be pi 1. And then there is, or pi negative 1. And then here's negative 1 pi. So if you were to trace this and put a mirror across, you would see these mirror each other. So if you wanted to, this could keep going, right? But that would not be a function at that point. So remember, restrict the domain to where it's always decreasing or always increasing in order to make sure that your function has an inverse.